Welcome back, AP Psych. We're starting our third video here on sensation and perception. So we've done our intro, we've gone over vision processes and perception. Our next sense is hearing or audition. This is the second sense that we're going to need to know the whole process of, the whole structure of the ear, how it transduces information and sends it to the brain. So that's where we're going to start. Similar to our vision notes, we're going to talk again about frequency. In terms of sound, frequency is the dimension of frequency determined by wavelength of sound, measured in hertz. Okay, so this is the same exact image as we had for vision, except instead of light waves, it's sound waves or vibrations in the air. So a short wavelength, the distance between peak to peak of the waves, high frequency, short distance between them, that's a high-pitched sound. The higher the frequency, the higher the pitch. The long wavelength with a low frequency, that's a low-pitched sound, right? Humans can hear sounds, frequencies from about 20 hertz to 20,000 hertz. We hear sounds best around 3,000 to 4,000 hertz, and that's where human speech is centered, which makes sense. On the other end, we have something called intensity or loudness, and that's measured in amplitude, the height of the waves, right? How large they are, okay? The more amplitude, the louder the sound. The smaller the amplitude, the softer the sound, okay? Loudness is measured in decibels, okay? So a few things to give you an idea of what a typical sound would be. In decibels, you can see our threshold of hearing, our absolute threshold, is 0 decibels. Whispers 20, typical room 40, normal conversation 60. As you get higher up to a busy street corner, you can see this differentiation line here, and that's at 85 decibels. Anything above 85 decibels, if you're exposed to that sound for a prolonged period of time, it can produce hearing loss, right? So if you're subway trains, jet planes, loud thunder, a rock band, amplified at close range. I'm sure some of you have been to concerts and you've tried to get as close to the front as you can. And when you leave that concert, you're like, yeah, I got this ringing in my ears, right? It's because you've done permanent damage to your hearing, and there's certain pitches that you're never going to be able to hear again as a result. So there's a lot of debate in scientific communities today, and there's some worry about young people because as the development of earphones has occurred, you've had these louder, higher decibel sounds directly next to your eardrums and to your ear processing for extended periods of time. So there's a worry that an entire generation is going to have some serious issues with hearing loss because of their exposure to those sounds above 85 decibels for prolonged periods of time. And if you get up to this range, loud thunder, rock band, like we said, one intense moment of sound can permanently damage your hearing. It doesn't have to be prolonged. Think about when you're young and one of your brothers or sisters or someone screamed in your ear and it was just felt like you needed to rub your ear, get something out of there. It really hurt. You damaged your hearing in that instance. So that's loudness of sound measured in decibels. Here's the ear. So this is the structure, just like we looked at the structure of the eye. You need to know the parts and pieces and how it works together, right? Just like the eye. Those are the two that we really need to know in depth. So the process. The first thing is our pinna. That's this part of your ear right here. Okay, it works as kind of like a funnel. It catches sound and funnels it down. Those sound waves come in to your auditory canal right here. And this is all the outer ear. Once it goes through the auditory canal, it hits the eardrum, which is also known as your tympanic membrane. If you're in band and you know a timpani, a big drum, right? You hit that and the top vibrates and it makes noise. That's just like your eardrum. It vibrates and it helps to process sound waves. So this is the beginning of what's called your middle ear. From the eardrum, it vibrates, and it vibrates these bones in the center ear, which are your hammer, anvil, and stirrup. And as those bones continue to vibrate, they continue the message, and they eventually connects through the stirrup here, or what's also known as the oval window, where it connects to something called the cochlea, which we'll talk about in a second. There's also in your middle ear these semicircular canals. They're fluid filled, and they control something called our vestibular sense, which as a major player in balance and coordination. Have you ever spin around and look at the sky and then you lay down on the ground and you feel like you're spinning, you're still spinning? We've all been on like merry-go-rounds or things like that as kids. That's because you've upset the fluid in your semicircular canals and your vestibular sense, your balance is all over the place, right? Until it settles out. But as that message continues through the oval window and the stirrup, it reaches the cochlea, right? And the cochlea is aware that sensory information is going to be transduced into neural signals that the brain can then interpret. Okay? There's something inside the cochlea called the basilar membrane, which has hair cells known as cilia that vibrate and are able to transduce, take that sensory information, turn it into neural signals, and send it up the auditory nerve to the thalamus, and eventually your temporal lobe and auditory cortex. Let's zoom in on the cochlea a little bit. It's coiled up. So in that previous image, we saw this coil here, kind of looks like a snail. This one is unraveled a little bit just so you can see the parts and pieces. But it's coiled, it's bony, it's fluid-filled tube in the inner ear that transduces sound vibrations to auditory signals, right? So those sound waves come in, hit the eardrum, vibrate those tiny little bones, your hammer, anvil, and stirrup, and that vibration goes into your cochlea, and the fluid continues to vibrate and stimulates your hair cells, right? Those little hair cells, and those hair cells are able to transduce that information so that it can be interpreted by your auditory nerve and taken and sent to, stopping at the thalamus, and then to your auditory cortex of your temporal lobe. Okay. So just like the eye and how the bipolar and ganglion cells take light waves and transduce them into neural images, your cochlea takes sound waves, transduces it into neural images so your brain can perceive what you're hearing. So there are a few theories of hearing, just like there were theories of color vision that we want to reference. The first is frequency theory, and that states that the rate of nerve impulses traveling up the auditory nerve matches the frequency of a tone, thus enabling us to hear its pitch. Okay? So if a sound frequency is coming in at 100 hertz, okay, it travels up the auditory nerve at that same frequency. This is the idea. And that allows us to hear that pitch. Right? If it comes in at 200 hertz, now it's traveling with a faster frequency, right? And it travels up at that same frequency, and that's what allows us to hear the pitch as well. That's frequency theory. The second, something called place theory, suggests that sound frequencies stimulate a specific point of the basilar membrane, resulting in perceived pitch. Okay, so that basilar membrane is what's inside the cochlea and contains the hair cells. So this theory contends that when sound waves come in, they hit a specific point on this basilar membrane, and that specific point correlates to a specific pitch, and that's how we hear it. So specific place theory is another theory of audition. Another term that's important to know, we have localization of sound. So we have two ears, and sounds reach one ear faster than the other, right? When you hear something coming through your left ear or coming through your right, we know where the sound is coming from based upon which ear it hits first. Okay? And that tells you, hey, I need to turn my direction this way or that way based on where the sound's coming from and what it's telling me to do. That's also why if you're trying to figure out, you hear a faint noise and you're trying to figure out where it's coming from, the worst thing you can do is turn your head both directions and start looking, because you've lost your localization. If you hear a faint noise, you want to stay still and see which ear it's hitting, and then you can start to figure out where it's coming from. Now we're going to get into hearing loss a little bit, something that we're all going to experience in life, unfortunately. But the older we get, we tend to lose the ability to detect higher frequency pitch sounds. You may experience this with grandparents or parents as they start to miss certain things or not hear you and say, huh, what's that? You speak up, right? The amplitude or the intensity, the loudness, right, of the amplitude of the sound waves required for perception relative to the 20 to 29-year-old group is shown here with other age groups. Okay, So your frequencies down here, the higher the frequency of sound, the more intense or loud it must be for you to hear it as you age. Okay? So you can't hear these pitches unless they are up to 100 times more intense as you get into those 50s and 60s. So your hearing is definitely goes into deficit at those points. A couple of types of hearing loss that we'll get into. Why do we lose the ability to detect the upper frequencies as we age? Well, due to the everyday sounds we expose our ears to, generally any sound loud enough to produce something called tinnitus, or the ringing of your ears, causes some damage. So we mentioned that earlier. If you ever had that moment where you hear a high-pitched noise in your ear and you're like, what's going on there? That's the last time you're going to hear that pitch, because your ears, you're losing that ability. Or if you've ever experienced an extremely intense sound and it hurts, you've damaged your ears. And over the years, small amounts of damage accumulates to the point where we've lost the ability to hear certain pitches. And that's referred to as noise-induced hearing loss. Something we all go through. Noise over our lifetime does this to us. But however, we also mentioned high-intensity sounds can actually tear off the hair cells of your inner ears right away. Right? So noise-induced hearing loss happens over time. You can also produce noise-induced hearing loss immediately. Right? If you're in the front row of that concert and boom, there's some massive loud sound and it hurts your ears right away, you've probably damaged the hair cells immediately. So here's an image. These are healthy hair cells, 3 rows of outer hair cells and 1 row of inner hair cells. These are in your cochlea in the basilar membrane. They're what able to transduce pitch and sound for your brain to perceive. And this is damaged version of those hair cells. So you can see what happens, and they're nice and uniform here. And here it's hard to even detect or see if they exist anymore. So you can see why taking care of your ears and paying attention to the loudness of sound that you're experiencing is important. A couple other forms of hearing loss. You have conduction deafness. This is hearing loss caused by damage to the mechanical system that conducts sound waves to the cochlea. Okay? The mechanical system that conducts those sound waves. So we're talking about the eardrum, the hammer, anvil, and stirrup, those mechanical pieces that allow the vibration to get to your cochlea. Okay, that's conduction deafness. It can be corrected with surgery or hearing aids. That's, older people have hearing aids. People who have experienced some type of damage to those areas can get hearing aids, and it can be corrected, and they can have pretty close to normal hearing ability. On the other hand, there's something called sensory neural deafness. Just based on the name, sensory neural, you should think of the neural signals in there, and that's what keys you into knowing that this is hearing loss caused by damage to the cochlea, the part that turns sound waves into neural signals. And those receptor cells, or damage to your auditory nerve, right? All that is involved in the neural process of hearing. This is also called nerve deafness. You might hear it. This is a permanent condition, unfortunately. There's no way to fix that so that you can get a normal representation of sound once this has occurred. There is, however, something called a cochlear implant, which you can read through some of the details here if you'd like, but essentially it replaces your process of hearing. And it's an implant. However, it does not restore normal hearing. It can give a deaf person a useful representation of sound in their environment and kind of help them to understand speech and hear things for the first time, but it's not going to be very clear, and it's not super effective in terms of restoring normal hearing. But it is a massive change for someone who would have been deaf up to that point. So you can kind of see what a cochlear implant looks like. You have a transmitter and a speech processor and a microphone. And those are just up here near your temporal lobe. And inside of your brain, there are these things that are called the electrode array that collects the impulses from those stimulators and sends them to different regions of the auditory nerve. So essentially, this electrode array is in your brain, in your temporal lobe, and it's replacing the job of the cochlea and the auditory nerve. The controversy around this, it's super expensive surgery. And because insurance companies claim that deaf people can function normally and they don't need this, it's oftentimes not covered by insurance. So it's hard for people to access, and there's arguments that there should be more accessible to people because it does improve lifestyle and allow people to access some sort of hearing that they'd never have access before. So that kind of wraps up our hearing or our audition notes. As always, take your time answering those questions. Make sure you get some details down, and let me know if you need anything in class. Thanks.